Hi everybody, today we're going to take a look at 4.5 L'Hopital's rule. This is a rule that allows us to evaluate limits of indeterminate form in a different way than what we learned back in chapter 2. So first, as a warm-up, we're just going to refresh on evaluating limits. The first one is a continuous function, so we can evaluate the limit through direct substitution. So we have 1 squared minus 1 plus 4, and we get 4. The second one, though, if I try direct substitution, 5 times 3 squared, or 45, minus 48 plus 3, that gives me a 0 in the numerator. And 3 minus 3, of course, is a 0 in the denominator. So this is that indeterminate form that we looked at in chapter 2, where we know that there's a repetitive factor top and bottom that we should be able to cancel and remove. And specifically, the factor has to be x minus 3 up top, which means that my other factor must be 5x minus 1. So then the limit here would be 5 times 3 minus 1, or 14. Right. That's the behavior of the graph at that moment. There's another way to evaluate this limit, though. So when a limit produces an indeterminate form of 0 over 0 or infinity over infinity, so different than all indeterminate forms, this one has to be fraction. It has to be in a fraction form. So we can use this L'Hopital's rule to find the limit, which says you can derive the numerator and the denominator independent of one another, so not the quotient rule. And you can do this successive times until you arrive at an answer. It is removing those repetitive factors is what it's doing. So that extra note here is you can apply this rule multiple times until you no longer have an indeterminate form. So again, it works on 0 over 0 or infinity over infinity indeterminate forms. So we're going to use L'Hopital's rule to evaluate this limit. So the first step is verify that we cannot use direct substitution. So just like before, we still want to double check that it is a 0 over 0. Because in this case, if it's not, you're going to arrive at the wrong answer. So 2 cubed is 8 minus 8 of 0, of course. 2 to the 4th, 16 plus 4 is 20 minus 20 is 0. So we can use the rule. So applying L'Hopital's rule is saying that the limit as x approaches 2 of x cubed minus 8 over x to the 4th plus 2x minus 20 is equivalent to the limit as x approaches 2 of 3x squared over 4x cubed plus 2. So at this stage, I would want to try to evaluate the limit again through direct substitution. And in the numerator, I would have a 12. And in the denominator, I would have 8 times 4 is 32, plus 2, 34. So 6/17. So the behavior of this original function at 2 is 6/17. Okay, next one. So it doesn't have to be polynomial-like or rational. With polynomials, it can have any type of function, really, as long as it yields that 0 over 0 or infinite over infinite in the beginning. So if I tried through direct substitution right away, by plugging in 2, I would have 4 minus 2 squared, which is 0, and sine of 2 pi, which is 0. Okay. So now applying L'Hopital's rule, says that the original limit is equivalent to the limit of negative 2x over cosine pi x times pi. Right, that's a chain rule, so we don't want to forget about the pi. So now through direct substitution, the numerator would give us a negative 4, and the denominator, cosine at 2 pi, is 1. So 1 times pi, or negative 4 over pi. So I'm going to leave this one, and let's try one with an e to the x. So quick check, do I get a 0 over 0? E to the 0 is 1, minus 0, minus 1, yep. Cosine at 0 is 1, minus 1, so yes, this is a 0 over 0. So then it is equivalent to the limit as x approaches 0 of e to the x minus 1 divided by negative sine x. So now I evaluate this one. E to the 0 minus 1, well, that's still 0. And negative sine at 0, well, that's also still 0, which means we can try again. So now it becomes limit as x approaches 0 of e to the x over negative cos x. So now if we evaluate, we have a 1 divided by a negative 1. Okay. And we can prove this graphically. If I were to go to Desmos and type this in and zoom in and take a look at what's happening at the graph at 0, there's some kind of a discontinuity. Should be a hole, right? It's a removable discontinuity. And therefore that hole should have 0, negative 1 as its ordered pair. So here's 3 U-try problems. Again, I'll leave these blank, and we'll visit them in class if you need help with them. They all start as 0 over 0s. You should be able to apply the rule and arrive at an answer. Okay. Now we're going to look at something that's quite different, but certainly relevant. So remember when I said L'Hopital's rule needed to start with a 0 over 0 or infinite over infinite. Here's a situation where I don't even have a fraction that I'm looking at, right? So I cannot apply L'Hopital's rule unless I do. But I do have some kind of weird, indeterminate, I'm not sure what the answer might be, scenario, right? X to the x power, 0 to the 0 power. I don't know, like I might say, well, that's 0. Somebody else might say, well, that's 1, because anything raised to the 0 power is 1. So we don't know what the answer is going to be. And this is also the limit from the right-hand side, which isn't a huge thing, but it's relevant here. So in the last chapter, we came across, with logarithmic differentiation, we came across this idea of if I have a variable in both the base and the exponent, I need to kind of separate them. I need to expand them because I don't have a rule that allows me to derive that. And we use logarithms in order to do that. So if I apply a log, then I can apply properties of logs and I can bump them out. The problem that I have here versus what I had in last chapter is I don't have a function. It's not two sides to the equation where if I apply a log to one side, I can apply it to the other. So I actually have to simultaneously apply an e to the something and an ln to the something because they are inverses. So we're going to apply both of them at the same time, which means that we're really just changing this by a value of 1. The reason that we're doing this, these are 2 important notes, we must have a fraction in order to use L'Hopital's rule. Right? Those are 2 key things right now. So I'm going to first work on, can I turn this into a fraction to see if L'Hopital's rule can be applied or not. So if I apply an e and an ln at the same time, and it's getting applied to this x to the x power, right? This portion right here, that's where the inverses are. They're really not changing my value, but it's allowing me to manipulate. Okay. the next line of work, I'm going to apply a property of limits that allows me to pull constant type terms out. Right, when I'm evaluating a limit, I need to get to those x's. I don't really care about anything that doesn't change the value of the x so much. So that e could be applied inside the limit or it could be applied outside the limit. It's like pulling a coefficient out. We're allowed to do that with limits and derivatives for that matter. So this is equivalent to e to the limit as x approaches 0 from the right of ln x to the x power. Okay, so now I'm getting somewhere again. This is also, in some cases, people might drop this e and ignore it for a little while. I don't recommend that because what will happen is you'll arrive at an answer, and the answer should be e to that answer, and you just give me the answer. So I would keep the e there, even though it looks kind of ugly and makes it messy. I would keep it there. So anyways, keeping going. Now I can apply my first property of a logarithm. Right, my whole goal right now is to write this as a fraction. I'm not looking to evaluate. I'm not looking to apply L'Hopital's rule yet. Properties of logs now allows me to bump down the exponent of the x. So now I have x times ln x. Okay, not quite a fraction. I'm still in this rewrite stage. So I can rewrite this as ln x divided by x to the negative 1. Right, I haven't changed the value at all. And now I have a fraction. And if I evaluate this at 0 from the right, it has to be 0 from the right, I would have a 0 over 0. Right, I have a, or really an infinite over an infinite, some form of indeterminate form here, because I would have asymptotes in both cases. Okay. So now that I have this fraction and I know I have my indeterminate form, now I get to apply L'Hopital's rule. Right, in both cases of these functions, numerator and denominator, I have an infinite discontinuity. I have asymptotes at 0. Okay, so applying L'Hopital's rule the same exact way, deriving the top and the bottom independent of one another. So I'm keeping that e so I don't forget about it. ln x derives to 1 over x. X to the negative 1 derives to negative x to the negative 2. Okay, so I'm going to simplify this so that I can kind of see what I have before I evaluate. So 1 over x is x to the negative 1. Now I can use properties of exponents, right? If I'm same basis separated with division, I'm going to subtract my exponents. So I would have a negative 1 minus negative 2 is plus positive 2, so negative x to the first power. And if I evaluate this limit, now that it's just a negative x, that right-hand side doesn't matter so much because it's continuous there. But before, the right-hand side mattered because of these asymptotic behaviors. So now, on the right, yeah, it's approaching 0. On the left, it would have also been approaching 0, so it doesn't matter so much. This limit is equal to 0. But don't forget about your e, because I really have an answer of e to the 0, which is equal to 1. Okay. So in red, in the beginning, I worked to create the fraction so that I could apply L'Hopital's rule. And then in blue, then I applied it, I simplified using exponents, and then I evaluated my limit at 0. There's a few of those in your homework, and if you don't come across them, then I'll make sure I go through them together with you to make sure that you understand that, especially the AP levels. Okay. We say that f of x grows faster than g of x, right, if the limit of as x approaches infinity of f over g equals infinity, right? And equivalently, if g over f then gives you a 0, okay? Right, so that makes sense based on those 3 rules that we learned back in chapter 2 as well, limits at infinity. Same idea. Now we're looking to see, well, which function is growing faster? And at first glance, you might be like, I'm not too sure, but we can use L'Hopital's rule to manipulate this and come up with an answer pretty quickly. So which of f of x equals x squared and g of x equals x ln x grows faster as x goes to infinity? So we could use either model. I'm going to go with more of the straightforward answer and put the f over top of the g. So limit as x approaches infinity of x squared divided by x ln x. Okay, well, right away I can simplify that. That's no problem. So I have an x over an ln x. And in this case, yes, it would be an infinite over an infinite behavior, so I can use L'Hopital's rule. So I derive each independent of one another. X derives to a 1. Ln x derives to a 1 over x. Okay, and if I simplify that, 1 divided by 1 over x, that's equivalent to x. So I'm looking at the limit as x approaches infinity of x, which is, of course, infinity. And because I got infinity and not 0, that confirms or tells me that the first function, the f of x, x squared, grows faster. Okay, so we'll leave one more of these examples for our notes to go through together.